If we want to predict how a physical system behaves over time, we have to establish a specific mathematical relationship. We need to define exactly how the system's current state dictates its rate of change in the next moment. The engine that codifies this relationship is called an ordinary differential equation, or ODE. It takes the rules of physical change and translates them into a strict algebraic formula. The most basic first principle of growth occurs when a system's rate of change is strictly proportional to its current size. The larger the system gets, the faster it grows, by a constant factor. This chart displays that exact proportional relationship, known as exponential growth. The differential equation driving this curve is y prime equals r times y. Under this rule, the physical consequence is immediate and aggressive. The system accelerates continuously, driving the population or energy or mass toward infinity without any upper bound. Because the physical universe contains finite space and finite resources, this unbounded acceleration eventually fails to describe reality. No actual physical system can accelerate indefinitely. To accurately model the real world, we have to find a way to translate environmental boundaries and physical limits into the algebraic structure of the differential equation itself. We can introduce a term called capacity, represented by the variable k. This acts as an absolute environmental ceiling, a strict upper limit on how large the system is allowed to grow. This chart shows bounded growth. Here, the differential equation has been modified. Instead of the rate of change depending on the system's current state, it is now strictly proportional to the remaining empty space, written as k minus y. The resulting behavior begins with rapid growth when the empty space is vast. But as the system approaches the environmental ceiling, the rate of change severely decelerates, flattening out just below the limit. Applied to biological systems, bounded growth has a mechanical flaw. It assumes a population begins at its absolute maximum rate of acceleration, when in reality, a small initial population takes time to build momentum. By multiplying the current state, y, by the remaining capacity, k minus y, we get the Verhulst modification. This produces the logistic growth curve, governed by the equation y prime equals r times y times k minus y. The logistic curve operates in two distinct phases. It starts with early exponential behavior as the population builds, which then smoothly transitions into a decelerating, bounded asymptote as the system detects the capacity limit. Exponential, bounded, and logistic models produce entirely different physical behaviors, yet they all share the exact same foundational architecture, an ordinary differential equation defining a rate of change. While altering the algebra successfully enforces environmental limits, the equation is incomplete. By itself, the differential equation does not yet lock the system into a single, specific reality. The primary limitation of a standard algebraic ODE is that solving it does not output one single fixed trajectory. It produces a massive family of possible solutions. Instead of drawing one path, the equation evaluates a specific numerical slope for every single possible coordinate across continuous space. This is a direction field. It provides a geometric visualization of all these localized slopes, plotting them as individual arrows arrayed across a grid. Each arrow represents an instruction, showing exactly which way a system would move if it happened to pass through that exact point. Together, they represent an infinite family of potential realities existing simultaneously. To lock this theoretical framework into a practical reality, we have to drop a specific starting coordinate into the field. This critical pairing, combining a governing differential equation with one fixed starting coordinate, is defined as an initial value problem. That initial condition acts as a physical pin dropped directly onto the direction field. From that pin, the curve obeys the localized slopes, tracing a continuous path forward, guided by the arrows. A completely different reality is generated simply by moving that starting coordinate to a new location. The differential equation defines the immutable laws of physics for the system. The initial value problem specifies the deterministic history and future of one specific universe within it. Classical physical modeling relies entirely on one core assumption. Establishing one specific starting state will yield exactly one specific end state. This is determinism. It relies on the strict inability of a system to deviate from its projected path. The question is whether the underlying mathematics of a differential equation actually enforce this assumption automatically. In physical systems, we observe bifurcation, where a single event hits a critical threshold and chaotically splits into multiple distinct diverging paths. It turns out that some mathematically valid differential equations will also completely fracture when subjected to an initial value problem. When a single starting coordinate yields multiple correct answers, the entire purpose of predictive modeling is destroyed. The geometric tracing of a path through a direction field is meaningless unless we can mathematically prove that absolutely no alternative paths exist within that same space. To test this, we can look at an autonomous system explicitly designed to mathematically break determinism. The equation y prime equals the square root of the absolute value of y. We construct the initial value problem by placing our starting coordinate exactly at the origin, 0, 0. To determine if this equation can actually be solved, we apply the first foundational theoretical check for any ODE, the Peano existence theorem. Peano's theorem outlines a core condition. It states that if the function governing the equation is continuous, then at least one local solution must exist. The square root function is continuous everywhere on this domain. Therefore, it passes Peano's test, guaranteeing a solution. This chart shows the first perfectly valid solution to our problem. Starting at the origin, the system remains completely at rest, yielding a flat line along the time axis. The math checks out. But a catastrophic failure in our predictive model appears when we look closer and find a second valid solution. A parabolic curve, 1/4 t squared, also perfectly satisfies both the initial state at the origin and the strict slope requirements of our differential equation. Because Peano only guarantees existence, the theorem exposes a critical gap. Continuity alone leaves a system vulnerable to fractured, non-deterministic futures. To rescue the validity of predictive modeling, we require a higher, stricter mathematical boundary. This is the Picard-Lindelöf theorem. It serves as the ultimate test for uniqueness in an initial value problem. For this theorem to hold true, the differential equation must be Lipschitz continuous. This is a non-negotiable mathematical condition. Lipschitz continuity acts as a strict speed limit. It dictates exactly how fast the calculated slopes in a direction field are allowed to change as you move from one point to another. By capping the rate of change of the slopes themselves, this limit geometrically prevents two valid trajectories from ever intersecting or branching out from a single point. If we look back at the fractured square root equation, we can immediately diagnose its structural failure. The derivative of the square root function approaches infinity exactly at 0. That infinite spike violates the Lipschitz speed limit, shattering the determinism of the equation. We can contrast this failure with the foundational growth models we examined earlier. The algebraic structures of exponential, bounded, and logistic growth rely on linear and polynomial terms. These terms easily satisfy the Lipschitz condition, keeping their slopes well within the required limits. By satisfying both Peano's requirement for existence and Picard-Lindelöf's strict boundary for uniqueness, these specific differential equations eliminate the possibility of fractured realities. They provide a mathematically guaranteed, singular, and perfectly deterministic vision of the future.